basically we try to do, I try to cover NV sensing for regarding the application to magnetometry. We will do it in two parts. The first one is the CW regime, where we have a lot of applications already. We just continuously drive the NV center, monitor the spin resonance, and measure the influence of the magnetic field on the OD, using the ODMR. And then we will see that you can do more advanced experiments and reach higher sensitivity if you do it in a pulse regime. And this is something I'm going to cover tomorrow, I hope, or maybe Friday, depending on what we do tomorrow, to prepare also the demo we will have. Okay, so this is the purpose of the talk today. And that will be, I guess, 1 hour long. And then we're gonna, I will switch to some illustration on this concept of NV magnetometry in this regime, regarding what we are doing now in the lab, in our lab, which is using this technique to probe magnetic and superconducting properties of materials at high pressure. So that will be more like a seminar-like presentation where I will describe our ongoing work on this topic and explain why we believe it's important to investigate these systems and why NV are really appropriate for doing these measurements. Okay, as you know, we have, yes, I asked yesterday a question. If we look to the G2 of a single center, NV center, we have this dome shape experiment, and there is different points that I would like to comment. The first one is that here, there is a kind of limit, and as soon as you measure something, if G2 is below 0.5, 1/2, you can say there is a single emitter. And the reason for that is the fact that for n emitters, then G2 at time tau equals 0 is 1 minus 1 over n. Okay, so if n equals 2, then I have 1/2. So it's a kind of basic threshold, okay? And that's the point. That tells us somehow, if I measure that here, I am at a level of 0.2 perhaps, let's say. So I'm clearly below that, and I can definitely say we have a single emitter. Now there is always some background in the experiment, so somehow the question when you do those kind of measurements is, do you take or not into account the background? Do you correct it or not? That's a kind of discussion that people can have. But what's also important is these features. And these features now we have it corresponds to a G2 value at that observed for this time scale, which is larger than unity. What does it mean physically? It means that actually, you have a bunching effect of the photons that are produced. And this is due to the shelving of the metastable state. If we look to the shelving of the metastable state, we have here our two-level system, that pumping rate R, a decay time by spontaneous emission gamma, but at the same time, the system can leak to the singlet state. I only put one level, but this is a doublet, as we've seen. And in this shelving state, during that, we do not see emission at this wavelength. Okay? So if you look now to the emission, you will have, from time to time, the photons that are emitted like that are anti-bunch. Anti-bunch means that if I have a photon detected, I need to wait a given time that I get another photons. And the time, if I'm in the low excitation regime, is simply 1 over the decay rate. okay, the spontaneous emission time. So those photons are separated in time, grossly, by a delay of the radiative lifetime of the emitter. Okay, but now, as soon as the system goes to the shelving state, then the emission here is stopped. And now, if I look to another time scale, and it's actually what I'm doing by doing this G2 measurement as a function of the integration time, then I see bunches of photons. The first bunches of photons here, and then another bunch of photons. And this is what produced this effect of the G2. And you can do a calculation about that and that was a way that was used at the very beginning to quantify those leakage rate, which were completely unknown. So people do use the G2 measurement to understand somehow as an insight of the photophysics of the NV centers, and that has been quite important for the following, and also to understand all this leakage. Okay, maybe now I should perhaps discuss this. Wait, yes? Yes. Or just because at the beginning people didn't know that there was only there were two systems. But basically, all this it's somehow the two levels that are here. It was just the model. But, so you can have different model and use them to have that. It's different possibilities. What you also need to perhaps I should mention that all these rates are not accurately known. They somehow, there's a large uncertainty about all these processes. And still people are just trying to investigate them. But it might depend also on the materials, on different properties. So the rates are known, but up to a given value, I would say, up to a given uncertainty. So as it was said, we have to do some evaluation of the course. So what we discussed with Professor Singh is that we would ask you to present a research paper. So you team up by four people, a team of 4 of you, and then you work together and try to understand one of those papers, and then you get something like 10 minutes of presentation, and we will have 2 to 3 minutes to discuss the paper with you. Okay, and then we do it with 8 teams. That means 8 papers. So I tried to select some paper that would somehow be complementary to what we discussed in the course. There are different things. Things that are more related to materials, papers that are more related to fundamental physics. So I will just describe them very quickly. The first paper here is a paper by Wartop, team by Jörg Wartop, where basically they demonstrated that you can enhance the coherence time, the T2 time of the NV centers, by removing the nuclear carbon, the carbon atom that have a nuclear spin, meaning the carbon 13. So you do a growth of diamond by CVD technique, where you have only carbon 12. And carbon 12 is nuclear free, has no nuclear spin, and they demonstrated that there is a strong enhancement of the T2 time in this technique. This paper is from Misha Lukin team in Harvard, and basically they demonstrated that they could use NV centers as tiny thermometers, perhaps the tiniest thermometer in the world, basically, and the nanodiamonds were integrated in living cells, and they could measure the temperature inside the living cells using those nanodiamonds, and the NV centers here. Here it's another, here it's from us. So it's a paper I already mentioned, but that could be a way also to come back to the GSD and all that and try to understand the system. So how we can use a FIB machine to produce NV center. This is a paper again from Wartop team, where basically they took a diamond slab and implanted N2 molecules. And the implantation of N2 molecules can lead to very close nitrogen atoms. And if you now convert them efficiently into two NV centers, those two NV centers will be so close that there is a magnetic dipolar interaction between them. And they observed this magnetic interaction, how it changed the spectrum. And at the same time, they could use address one and drive the other one through a kind of CNOT gate. So you have one qubit, which is one NV centers, acting on the other qubit, which is the other nitrogen NV centers. Unfortunately, it's a very nice scheme, but it cannot be scalable. Up to now, no one has really been able to establish it as a scalable system. But nevertheless, I think it's quite interesting to discuss and to know this work. This is by us. So it's what we called, it would be an illustration of what we call wide field NV magnetometry. And I will just give you a few slides and you will see how it works. And then there is a lot of discussions about that and why it was perhaps important to have those microdots. They were designed actually by colleagues at the Institut Curie in Paris. We want them somehow to be integrated into anvil cell. And after you want to be able to move these micromagnets inside the cell using an inhomogeneous magnetic field. This is also by us, where basically what we've been investigating. It's I always mention that the NV centers is along the axis of the NV centers. Now, what happens if there is a magnetic field as a strong transverse component? Actually, that transverse component will mix up the quantum state, and that has some drastic consequence on the ODMR signal and the measurement stability. But you can use them in a way to have a microwave-free detection. And this paper is from our colleague from Thales. So this is a very clever idea about using the NV centers in an homogeneous magnetic field to have as a real-time spectrum analyzer. And for many applications, namely for radar, what you want to have is a complex signal, radio frequency signal that arrives, and you want to analyze it. But if you have the standard way to analyze a radio frequency signal, usually you will mix it with a local oscillator and do the measurement, and you sweep the local oscillator. That's the standard way we do spectral analysis. And that's a very different technique. Basically, you want to have a snapshot in real time of the spectrum. And you will see how this can be done with the NV center in the paper. And this is something a little bit different. Again, it's from us. So I'm sorry I put a lot of paper by us, but just not by, there are many other people that have done that, but just because I know them also. So, so it will be also easier to discuss with you and maybe also to help you during the preparation stage. We said with Kamal that we will have the Friday morning free, and you can work, and I can come and discuss with you to help you to prepare the system, your presentation. And this is how you can use the T1 time of the NV centers to measure, for instance, the occurrence, the coupling to gadolinium ions and quenching parametric species that will, and this has been, there have been a lot of applications in biology on following these ideas of what's called relaxometry. So how you come quickly to thermal equilibrium as a T1 measured by the T1 time, depending on the environment. And you can use this measurement to somehow get information about the environment. That's the idea. So I hope this will give somehow a kind of there's a lot of things that are now being done, and so many teams are working with NV centers at the moment worldwide. But somehow this will perhaps give you an idea, an overall view of the different developments that are ongoing at the moment. There are other things for sure. I do not want to be exhaustive, and that would be too long and perhaps not so interesting also after each topic by itself. Okay? So now perhaps on the NV, we come back to NV magnetometry, and also how we can use somehow the NV as spin qubit. So as I mentioned, you can do a very simple experiment on NV center, on single NV center. You have here a sample. On the sample, all these spots correspond to single NV centers. And then you have to put the microwave drive. And the microwave drive, there's a lot of possibilities to do it. One very simple one is just you simply put a wire, a copper wire, on top of your sample, and you drive through this wire the microwave signal. And the microwave signal will have an orientation that can induce the precession of the NV spin and produce a magnetic resonance. Of course, this is quite simple. What you can do is then lithography, deposit a metal and some antenna if you want. So there's a lot of work also about engineering the microwave field for doing that. But somehow for a demo experiment, this is far enough. So you just take that. You can have a microwave synthesizer, and for many experiments, you want to control the time during which you apply the microwave to produce pi pulse or pi over 2 pulse. So this is done by simple components like mini circuits switch that you can use between the synthesizer and what we call the antenna that produce the microwave field. And now, for instance, what you can do is claim or add an external coil or a permanent magnet that will produce a small DC magnetic field that will change, that will split the level of the NV centers. And the NV centers is detected as previously. Green laser is used, focused on the beam to excite the NV centers. Then we raster scan the sample to find those, the NV center dispersed in the diamond. And the light that is emitted by the NV centers are collected by the same microscope objective. Then there is what we call the dichroic mirror. This dichroic mirror filters the light that is emitted by the NV centers from the green laser excitation, because as we know, there's a Stokes shift that corresponds to the luminescence of the NV centers. Then you focus it on a pinhole here, and the pinhole ensures a confocal detection. That means that you reject the light coming from most of the diamond sample apart from a few microns around the sample, the NV center, the focusing point of the microscope objective. And then you do a detection that can be a G2 detector, G2 measurement, and then you have a beam splitter and two avalanche photodiode that operate in photo counting regime, or you have simply one and you register the number of count for a given integration time so that you monitor in real time, you monitor the intensity that is emitted by the NV center, and then you simply measure the intensity level as a function, for instance, of the microwave frequency. Okay? So doing that, it's a very simple system that you can build, and maybe we'll see that, or I will show this afternoon, and I will show you also by video what is in our lab. But it's not so difficult to do. Then we apply a field of 20 Gauss, for instance, that will create the splitting of the NV centers, and now we can address, for instance, one of the transition from 0 to ms equal -1 or 0 to ms equal plus -1 by choosing, by scanning this frequency and being on resonance of those well-separated system. And now I have a qubit. I can see that as a qubit, a two-level system associated to the spin 1 that I can manipulate using the microwave and detect using the light emission. Okay, so now all the process I'm going to describe are based on the combination of microwave drive plus the time window where I will do the detection of the luminescence, because all the detection has to come from the luminescence of the NV center. So one very simple experiment is to show, for instance, how we can have a spin state readout. So let's do the following thing. Let's start with the laser here. The first laser pulse that is here, I will try to follow it. That's the first laser pulse, 1. This first laser pulse, will polarize the system into ms equals 0. So I apply a pulse with enough power and long enough so that the system is now within, and a few microseconds is enough for that, the system is now pumped into ms equals 0. Okay? And now I just do nothing. What happens? And I will come back to the thermal equilibrium, because now the system is in the dark. Okay? So I will populate initially the system from to the ms equals 0 state, which has the highest luminescence level, I remind you, and then I wait. And then what I will do is that I have now a second pulse, which will be laser pulse that I will use as for the readout. So then I will measure the intensity emitted during this short laser pulse, and as short as possible, but long enough so that I have enough photons to know, to discriminate, to have a relevant information for the intensity level relative to shot noise. Okay? And what do I see? It's this first curve, this curve. So what I see that first the system goes up. And why does it goes up? Because, of course, I am in the 0 state. The 0 state is bright, very bright, so I have the high intensity level. And what happens then is the fact that the system will leak again. We have, to be honest, this system, so this will be ms equals 0. That will be ms equals 0 on the other side, but that will leak a little bit to the ms equal, that won't stay for long enough in the ms equals 0. There will be some decay, but this it doesn't matter. I will repump them, but with that will be. So when there is this leakage here, then the system will progressively, or at the same time, I'm sorry about that. I should mention that here. The system will, in that case, also somehow it's in the dark. So it will there will be again a new population coming to ms plus -1. Okay, there is interaction with the system so that somehow you come back also to the ms equal -1 system. So what you see is a decrease of the intensity. Okay, and the decrease of the intensity occurs within a few, typically within a microsecond. Now, at the same time, what I can do is something a little bit different. Or independently, what I can do now is that the second experiment. In the second experiment, I have here the laser, again the readout as previously, but now in between, I apply a pi pulse. The pi pulse transfer the population to ms equals 0, to ms equal -1. Okay? And since I'm in ms equal -1, I have this is the blue curve that I have here. I have a very weak signal coming from that. Okay? I have less intensity coming from the ms equal -1 signal. And this difference is simply the measurement of the different leakage. And then what I will do is that the system will go to the metastable state. Once it's in the metastable state, it cannot emit photons anymore. And after that, then it will again, the metastable state will leak toward the ground state. And then at the end, again, I come back to the thermal equilibrium, where the population is now at the same level on ms equals 0 and ms plus -1. And somehow the contrast that of my ODMR measurement is this window, everything which is integrated here. Everything that is integrated in this window is proportional, will give me the ODMR contrast. So that experiment tells me that somehow I have a kind of preferential, if I now look to, I can do it, I can do a kind of curve where somehow as a function, if I do a CW experiment, what is the good? What is what will be the optimal value of the contrast? The optimal value of the contrast will be all that integrated in time. Okay, but I can do also a time window where I will measure somehow the contrast for if I want to have an accurate detection. And the time window that somehow, if I change the time of measurement for the spin determination, and will be as a function of the contrast between the two things, I will have something like that. Okay? And somehow this is something where this, at the beginning you have no information, that increases, then there's a kind of optimum, and after a while, of course, if you integrate too long, but you mostly see the thermal equilibrium and it comes back to 0. So somehow in this very simple experiment, you have a lot of things to understand regarding the mechanism of the polarization process. And it's another way also to understand or to measure all the different leakage rate. And this is adapted from that paper and from Anaïs Dréau thesis. Okay, now somehow this tells me how I can do. So one thing I will do now is to measure the Rabi oscillation of the system. So I remind you that the Rabi oscillation is the coherent drive of the spin. Okay? So I start by a laser pulse here of 2 microseconds long. This is my first pulse here. Basically, this is just intended to polarize the signal. Okay? So here, after that, I know that I am in the state, the spin state is in the ms equals 0 state. Okay? Then I wait, typically 1 microsecond. Now, I will apply the microwave pulse resonant with the transition between the two states, maybe ms equals 0 and ms equals -1, as I said previously. Then I don't know where I will land, depending on the length of the duration of that microwave pulse. I can do a pi over 2 pulse, I can do pi pulse, I can do a 3 pi over 2, 2 pi, etc., etc. But then I do the measurement. Again, that's not a projective measurement. I will have to repeat it many times to have enough photons to have a reliable experiment at the end, a reliable measurement at the end. But then I reapply the same pulse. So somehow that's the new pulse acts as the first one. It's a kind of, it reinitializes the system. But I can now use a well-defined probe, so time window within this pulse, that will be my readout, as I explained previously. So now I can say with that the number, the population difference somehow, this signal will tell me, would give me a signal that is proportional to the difference of population between the two states that I address by the microwave. Okay? So that will be here 1 and 2, and that, or maybe 1 here and 2 here. and then that will be the population difference. And this readout by the intensity of luminescence is somehow proportional to this information, to this difference of population. And of course, and then I wait, and at the end of the green laser pulse, I'm again in MS equals 0 state, so I can then take that into account, use this now as the reference intensity level, and what I have at the end, by just comparing the two signals, I have measured the population rho 11 minus rho 22 divided by rho 11. Okay? Then that would be equal to unity in my case. Okay, that's at the reference. You follow me? It's okay? So I do that, and then using that, you see that appears the Rabi oscillation, depending on the time t that is used for applying the microwave. So I can really see in real time on a single electronic spin the Rabi oscillations that is induced by the microwave field. Now, if I reproduce that for a long time, what do I observe? Depending on the microwave field, of course, as we have seen in the first lecture, the Rabi oscillation has a frequency that depends on the strength of the B1 field, if I use my notation of the first lecture, the driving microwave field, magnetic microwave field. So that I can control. It's simply the microwave power that I send in the antenna, basically. And depending on the microwave power that I send, I can choose either a weak magnetic power, and then I will see long oscillations, small with a small Rabi frequency. And now I can also increase the microwave power, and then now fast Rabi oscillation, the Rabi frequency has been increased by the microwave power. But at the same time, both signals, as you see here, decay, and they decay on what is the time scale of the decay, comparing to the parameter that we've seen. We have three possibilities, T1, T2 star, T2. What you would say? Sorry? T2 star, exactly. So the decay here, it's at T2 star. But you may ask yourself, it is strange, I'm working on a single spin. I told you before, the T2 star was in a standard NMR experiment, was associated to an ensemble. And this ensemble, being in an inhomogeneous magnetic field, with slight difference of the magnetic field, will somehow precess a different frequency, and then there is the scrambling of the signal, of the overall signal, that is due to that. Now I have a single spin. Can you explain me why I can nevertheless speak of T2 star in that case? Usually T2 stars in NMR is defined for an ensemble. Here I have that, but I do agree it's not the T2, it's the T2 star. And basically it's what you see. The T2 is going up to 2 microseconds in this experiment, the value, the decay time. And this is more a T2 star experiment. And the point is that if I have a single spin, T2 star, it's somehow, it can be associated to a jitter of the line. So somehow there is it's a process that will somehow, my spin resonance, the spin resonance of a single NV can nevertheless wobble a little bit. So you can imagine like a laser. In a laser, we have two, if I speak about the line width of a laser, I have two types of line widths in a laser. The first one is called the shallow tones limit. It's a fact, it's linked, it's fundamental limit, where you have a kind of, it's associated to the spontaneous emission, okay? And it's a little bit the same. We have here a fundamental limit that will be set by the T2. The T2 is, for instance, the nuclear spin nearby that will control the magnetic, that will induce some noise on the magnetic field and modify the spin precession. But you also, in a laser, it's very hard to be at the shallow tones limit. Usually, you have a cavity, and the cavity can have some fluctuations. So what you see in practice for a laser, it's this image of a narrow line that jitters. Okay? And of course, if you now integrate that in time, the actual line width will be the jitter convoluted by the natural line width. And at the same time here, we can see our NV centers as a narrow line associated to the T2, which a width of proportional to 1 over T2, and at the same time some jitter. And the T2 star is a convolution of all those processes. Okay? And the jitter, we will see how we can control it. The jitter somehow can be controlled by some echo process, a little bit like before. So this is the kind I can also measure the T2 star time by exactly the same way, but perhaps more accurately, in the following process, in exactly what I mentioned before. It's a free induction decay experiment. But then what we do is what we call Ramsey fringes. And Ramsey fringes is we start by initializing the system in ms equals 0. We apply a first pi over 2 pulse. The pi over 2 pulse puts the system in a coherent superposition of the two states, okay, ms equals 0 and ms plus minus 1, let's say. And then we wait. If everything goes well, this coherent precession will now precess around my magnetic field, and I can measure I can reapply after that a pi over 2 pulse. So if nothing happens, no decoherence process happens, then I have a pi over 2 pulse, a pi over 2 pulse. That's somehow equivalent to a pi pulse. So then I will have transferred the population from 0 to 1. Not exactly, because there is a time difference. So somehow if I take into a time difference, I will be able to get some modulation of the population. We will do the calculation tomorrow about that. So I see some fringes, and the fringes will decay on a time scale of T2 star. Okay, because of course, if there is any jitter of the line of the NV center, this will scramble the influence of the second T2 pi over 2 pulse compared to the first pi over 2 pulse. I applied the second pi over 2 pulse because I want to check if it's still coherent regarding the application of the first pulse. And somehow that would be equivalent to a pi pulse. Not exactly, because there is a phase that has appeared in between. So it's, then I would see some modulation of the population. But the amplitude of the modulation that are here will decay, and it will decay within the T2 star time, since then the second pulse see a state that has been strongly modified regarding the coherent evolution. When I look at time, we will do the equations tomorrow. We'll try to do it. But first, I want just you to understand them by hand. So now we can look to these specific time, which are very important because somehow they will give me the line width of the spin resonance. The spin resonance, if I take that, for instance, I do a Fourier transform, and that will be the line width of my resonance. Okay? Now we will see tomorrow how we can use this scheme of Ramsey fringes to measure a magnetic field that is applied within that time. And we'll see that this is not possible. This will simply be a phase shift of the system, of the Ramsey fringe. Okay, so once I'm here, I can start with a HPHT sample. So if you remind, this is the yellow sample that I showed at the very beginning yesterday. The nitrogen content is around 100 ppm. Carbon-13 is a natural abundancy, 1%, but this is somehow negligible. What matters is the nuclear spin, the electronic spin bath of the nitrogen impurity. Those nitrogen impurities have a spin, electronic spin 1/2, and it's this bath that will control somehow the T2 times. And the T2 times will be much shorter than 1 microsecond. So for instance, if I take nanodiamonds, the T2 star will be a few hundreds of nanoseconds for NV centers embedded in that. So to increase the T2 star, what you go is to remove the nitrogen impurities as much as possible as you can. So you work with a nitrogen content that is part per billion, and you can show that now the T2 star is limited by the carbon-13, the nuclear spin of the carbon-13. And that's around 1%. And that corresponds to a rule, an experimental rule that tells you that the NV concentration times the T2 star is about 3 microseconds times part per million. So if I have now an NV sample like that has a concentration of about 1 ppm, 2 to 3 ppm, the T2 star will be around a few microseconds. Okay? And we will see that tomorrow also in the demo experiment. Now what I can do, and this is one of the papers that I propose in the list, is to reduce the carbon-13 abundancy, and then we go from this to this. So now it's a sample that is grown only with carbon-12. So we take methane, so it's a plasma, in which instead of injecting methane with the natural abundancy in carbon, you have produced methane only with carbon-12, and that people know how to do that. It has been purified. And then with that, now you can significantly reduce by 2 orders of magnitude the number of carbon, and then you significantly increase the T2 star to about 100 microseconds. And somehow all the NV practical magnetometers are now built from those materials in which you will have a concentration of NV which will be of a few ppm within this carbon-12 environment. Okay? And that sample that becomes now expensive because, of course, you need this special isotope selection somehow in the methane gas that you will use, and this is quite expensive. So it's not, so then you have to discuss whether you need that or that, because the cost of the sample will be significantly different, and that's of course important for going to industrial applications. Okay, now I want just to give a small hint about the NV magnetometry. What matters somehow in all our experiments is the width of those peaks. Okay. And the signal to noise associated to the width of those peaks. And that somehow depends on different factors. So we made a few years ago a model for this CW magnetic sensing on a single spin, and it has been adapted for ensembles by Ron Walworth and his team in Harvard, where basically I tried to explain a little bit the model. So I think it's rather, it took us some time to do that. So basically, that's also in the thesis of Anaïs Dréau and in this paper. So basically, and it was done with Vincent Jacques, we applied, you have different rates. You have population rate, and population rate, that means that you transfer the population to the different states. And there are also the leakage. And at the same time, you have the coherent drive by the microwave on the spin here. And in the experiment, we just use a magnetic field to address only two transitions. It's simpler. So somehow you have different things. You have different parameters. You have parameters that are intrinsic to the diamond. For the population, it's the spin relative relaxation, T1 or gamma 1, which is in the millisecond range. At the same time, we have what is a coherence. So somehow, if you build a dipole here, a magnetic dipole oscillating, how long it will survive due to the magnetic environment. And then basically what matters is the dephasing gamma, but also gamma 2 star, okay? Or the inverse, this is 1 over T2 star. Okay, and this taking into account the value that we have before would be of the order of 10⁵ per second. And then you have also the rate, because each time that you have some pumping here, optical pumping effect, of course, you erase the magnetic dipole. You transfer to the excited state, so the coherent, so the dipole has been completely erased. So for that, we have, it depends on the pumping efficiency, so simply the intensity of the laser here divided by the saturation intensity on this electronic transition. And so we have different rates. The rate for the population is how fast we polarize in the system, and we have also to take into account the influence of the singlet manifold or the leakage to the singlet manifold, where the system will survive during a time of about 200 nanoseconds. And there is also the influence of spontaneous emission that will bring the system back here. And as soon as you bring back here, you can reestablish the coherence of the magnetic, you will have the magnetic drive. So there is a competition between all these processes. The pumping process that are somehow a reset of all coherent magnetic interaction, and at the same time, the magnetic interaction that will be used to produce a microwave resonance and somehow the peak of the ODMR signal. So if you do that, then you write out some block equations. So it's standard equations adapted from the formalism, for instance, of a two-level atom interacting with the driving field. But you add now the non-coherent process that you have to take into account that would somehow erase either the population or the coherence of the magnetic interaction, the dipole, the magnetic dipole. And at the end, using that, you can find a compromise between the different, the influence of the laser and the microwave power and magnetic field, and demonstrate that typically the sensitivity in this DC scheme, where you simultaneously apply the microwave and the laser, is around the microtesla by already optimizing the best. So getting a few microtesla, it's somehow the good, what you can reach with those kind of system. Okay, on a single NV. Now you can increase it a little bit if you have now more NV centers, because of course the sensitivity will go as square root of the number of your emitters, because then you have more photons to detect. So, but that's the kind of system that we can have. So if we want to have higher sensitivity, so for instance, targeting the picotesla and even below, we need other schemes. And we need really to enhance that. Then we will apply a pulse scheme to avoid at least this kind of competition between the pumping by the laser and at the same time the coherent drive of the magnetic dipole. Okay? So but the DC scheme can be very important for many applications already. One of the first one that was developed, proposed and developed, the first realization was done in Jörg Wartrup team, was to attach a nanodiamond at the apex of a tip and use that to monitor the stray magnetic field produced by a sample here. And using that, you can really now, by scanning the nanodiamond, you can really map the stray magnetic field with an accuracy which is remarkable, that can be below a few, that can reach a few nanometers. What is also important is that you measure the field that is average on a volume which is typically the size of the NV center, and the size of the NV centers is nanometer. So you average the sample over this volume, and again, an important feature is the fact that this nanodiamond is non-magnetic. Otherwise, you would see the response of the nanodiamond. But since diamond is non-magnetic, you only see the NV center that is inside. And also that works in ambient condition, and the magnetic, so you compete somehow with another technology that was developed to measure, to map magnetic field at nanoscale, which is called magnetic force microscopy. So this is a magnetic cantilever, and due to the interaction of this magnetic cantilever and the magnetization of the sample, you have a bending effect, and you measure this bending, and you could map the system like that. The stray the magnetization like that. But in this case, you have a strong back action because your tip is magnetic, strongly magnetic. And somehow there is a lot of bias and parasitic effect associated to the magnetic properties of the tip. Here we have a tip that is non-magnetic, no back action on the system. And this is described in length in this review paper. Just the sample that was, the system that was built in the team, what was here was a thesis of Loïc Rondin, where we have now the sample is here, and of course most of the magnetic sample are non-transparent. They are metallic or a garnet or whatever. So you do not see through them. So what we did was to have a system in which we could polarize the NV centers and detect at the same time, which was not the configuration that was used in the first demonstration. Nevertheless, what we have here is scanners. So we can scan the sample on XYZ with this piezo stage that you see here. It's piezo stage from this company, AtoCube. So we designed the system somehow with them. And there are 3 other scanning stages that are used for positioning the AFM tip. And the tip you don't see, but was somewhere here. And you have a nanodiamond that was grafted at close to the apex of the tip. And then the distance was about 1 millimeter, about approximately, which was enough, nevertheless a little bit challenging, to position the AFM tip in between the sample and the microscope objective. And this is a kind of image of the tip. So it was a very specific tip that had that shape so that we could really plunge toward the system and have this configuration. So what we see is that the resolving power is you want to measure, to have a resolution as close as possible to the nanometer range. But what matters is what set the limit of the resolving power. Suppose that I have two, I want to, the resolution I will have on the mapping of the magnetic field will be 5 to 100 of nanometers. And this is simply due to the height of the nanodiamond with respect to the apex of the tip. And it's very hard to put the nanodiamond really, really at the apex. There's when you glue it or you attach it just by forces, spontaneous forces, basically the nanodiamond will remove, so will go up. And at the very beginning, we tried to somehow use very tiny nanodiamond. It was quite difficult. But then we realized that due to this effect, we could work with larger nanodiamond, and somehow that would produce the same effect. But they were larger, easier to attach, and the strength was also stronger. The bonding strength was stronger. And the sensitivity is limited by, of course, the coherence time of the NV spin, but also the photon collection efficiency. And what has been remarkable is that people have been able to produce diamond tips. So you start from a diamond crystal, and then you shape using lithography technique and etching technique. You shape really tip from that. That can be attached now to scanners. And what you have here, it's you see here the diamond here, and on here there is the diamond tip that has been really shaped, curved into on the diamond sample, and on the apex of the tip there is an NV center. And that's really remarkable technological achievement, but that led also to a much more practical system and with more control, because now, for instance, you know the orientation of the NV. You can now even purchase tips that are grown, that are realized from 111 material. So, for instance, the NV is perpendicular to that, and that will be very sensitive to a stray field along this direction, for instance. Or you can purchase P tips that are in 100 direction, and the NV will be like that. So very sensitive now to in-plane magnetization. So you can really choose a lot of configuration of the tips that are available. They are very expensive also. A tip of 111 material will cost around 4,000 euros, and you can imagine how easy they are to break. So, okay, it's a good business somehow. And there's two companies, another one in China also, but two European companies that now sold these NV scanning magnetic microscope, Qunami in Basel and Cusabre in Zurich. Both are Swiss companies with different approach. Yes?
How many NV centers are in the...
So you do it with only one NV centers. So now there have been chips that are produced with two NV with the idea of trying to implement gradiometry. Because sometimes it's very interesting to have the gradient of the magnetic field. And you have two NV, you can have a signal that will produce the gradient. But basically, it's one NV. So what I want to describe, it's another approach that we developed with my colleague Thierry Debuchert in Thales, which we call wide-field magnetometry. This has been also developed in Harvard by Ronald Walsworth and his team. And it's somehow a much simpler system. So in that here, we will not rely on the resolution. Our goal is not to have to reach super resolution. We want to see the stray field with a resolution of about in the micrometer range, but we want to do it as fast as possible compared to the scanning system. The scanning system is great, but of course, resolution means also a lot of acquisition time. And now, for many applications, it's not what you want. You want to measure the stray magnetic field of samples that have typical size of a few micrometers. And for that, there is another approach, which is interesting and provides you with a lot of sensitivity. And we call that wide-field magnetic imaging, or quantum diamond magnetometry in the AOS. So the idea is quite simple. We have a sample here in which we have on top of it that will be put just right on the magnetic sample. We will have a very thin layer of NV centers, okay? And what we can do is now excite this layer of NV centers with green laser light. We can do it by two ways. The first thing is here we would put a dichroic mirror, and the dichroic mirror we shine through the microscope. But somehow, if for certain circumstances, that can induce heating of the sample itself. And if you want to avoid that, you can use another trick, is that you have total internal reflection in the diamond, which has a huge index of refraction, 2.4. And that's not so difficult to realize. And then you're sure that somehow what you will have is just the evanescent wave, and that will decay very quickly. And if you are a few micrometers above the magnetic sample, you do not care about the intensity. That's a possibility. Now you have this diamond layer. You have the microwave excitation. So a very simple way to have this microwave excitation is simply to apply now a magnetic this coil, and this coil you drive current, the microwave current with it, and that will induce the precessing dipole. That will be our Bx field somehow in our experiment. Then you collect the light that is emitted by the layer of the NV centers, and you focus it onto a CCD camera, very simple. So you have the image of the NV layer on top of the magnetic sample, and at the same time, to remove any green parasitic light, you just put a bandpass filter, or notch for combination notch filter that removes the green laser excitation and select only the NV luminescence. And I will show you how does that work with an array of permalloy microdot. So these are very thin, very soft magnetic material that can easily be magnetized with an in-plane magnetization, for instance, and it's what we're going to detect. Each plot has a typical dimension of 30 by 30 micrometer, but it could be much lower, and we will see much smaller, and we'll see example of that. So you have here an image. You see the dot here. That's the dot that you see here, okay? And here you have the image of the coil. It's taken really through the microscope objective. You see also that's the microwave coil. Huh? That's the coil here that you see. So what we see now, we apply the green laser, and you see the luminescence. We use that image was taken using this system, and you see really the light just emitting the layer of NV centers above one of those dots. And the dots were produced by our colleagues at Institut Curie. So I will show you now what we will have. Basically, the idea is very simple, and I hope that tomorrow we'll be able to show you a live demo experiment. So we simply now scan the frequency, and for each set of each frequency, we just record one image. So, and the image is just the luminescence of the NV centers that will be modified by the combination of the magnetic field, the stray magnetic field you want to detect, plus, of course, the microwave frequency. So what you have when we scan the frequency, these kind of things. You see some very strange shape that appear. Well, you would say that there's not much information around that. Actually, there is a huge amount of information in this set of image, and I will try to explain that. Okay? So why? In the NV center, we actually have 4 orientation. We choose, for instance, a 1, 0, 0 sample. So we have 4 NV orientation. For each, now if we look to 1 pixel, we can now use our set of image to now have pixel per pixel the microwave spectrum. So now this is what we would get, for instance, on one spectrum, and we would see, for instance, these 8 peaks. And these 8 peaks corresponds to the ODMR signal associated to the 4 possible orientation. I told you that what matters is a projection of the magnetic field onto the NV axis. So in our case, we have 4 projections of the magnetic field, and each of those projections will induce a splitting. So that's for one family. The blue peak here correspond to one family. The orange one to another family. The green one to another family. And the yellow one to another family. So from that, I can extract now 4 correlated measurements of the B field, of the vector B field. And I can use now, provided I have some information to remove some degeneracy in the response of those families, I can retrieve the 3 components, Bx, By, Bz of B. So this system allows me to measure directly the 3 B. So it's a vector magnetic field measurement. And this is very important. And this will bring a lot of information, as I will try to discuss. And another great advantage is, of course, associated to the fact that your time of measurement, you record the signal coming from all the pixels during the same measurement time. When you do a scanning experiment, you split your measurement time in a lot of tiny windows where you record the signal. So since all experiment have sensitivity which is set by the recording time, you want to have resolution. It means you have to spend time for doing that. In our case, we set a resolution which is about approximately the one also that will set by the distance of between the NV layer and the magnetic sample, but that can be as low as 1 micrometer, and then then the resolution somehow taking also into account the resolution of my microscope objective using the experiment, but it's not difficult to get a few micrometers of resolution, which is already great. But at the same time, the signal you have now has a huge signal-to-noise ratio compared to even a confocal scanning experiment that would somehow cut the time measurement in many small windows. So you have this multiplex advantage, and I will just show you now that it is a really quantitative. We can make really a measurement of the magnetization. So for instance, we have here the model of the micromagnet of this microdot. We apply an in-plane magnetic field that will induce in the micromagnet a magnetization. So you have a magnetization like that, and what it produces, a dipole like that, on in-plane dipole. If now I look to the magnetic field, I know that the magnetic field will do something like that, okay? We'll have this shape. And now what you see here, for instance, if I put on top of it the NV layer, what I will see, for instance, is in this direction a magnetic field like that, and in the other direction a magnetic field like that. And it's exactly what you observe here. You see the component of the magnetic dipole, of the magnetic field created by the magnetic dipole, with the magnetic field Z components going like that and turning around the dipole and going in the opposite direction on the other side. And now also I can have the two measurements, and what I can do from that is fit those images by just a quantitative measurement of the magnetization associated to the magnetization that is produced in the dot, and you have a lot of tools of micromagnetism for doing that. And you can, at the end, measure a magnetization and at the same time determine the height at which we have the measurement. We realize the measurement, and that can be reduced. Somehow this parameter will set the resolution of your measurement system. And this parameter, which of course is correlated to D, the closer you will be, the higher the sensitivity, will set also the sensitivity regarding your magnetic measurement. And this is, when you say that, this is equivalent to 10 to the 13 Bohr magnetons, or 10⁻⁷ mu, and this is the sensitivity of a commercial squid. Actually, this is the signal we measure, so we are far above the limit here, but this is already the sensitivity. This is the limit sensitivity of most commercial squid apparatus that you can purchase. So you have a very simple system that somehow allows you to beat the sensitivity of a squid, and that is what explained in this system. And there are, I will show you later, after that, a lot of advantages of this technique in the very specific context of high pressure measurements. I will just finish very quickly because this is not long. So what you can do with that, you have a lot of possibilities that this opens. You can investigate micromagnets. It's quite interesting, actually. People are doing a lot of magnetic materials at microscale. There's a full chemistry. Many chemists are working on that. What you can do also is to detect the magnetic field which is created by a wire. And what you have here, it's the map extracted that is reconstructed from the current flowing in a wire. It's not so interesting, but you can apply the same thing now to detect the magnetic field produced by current in microcircuit. And this is something that we have done also with Thierry de Buchert and people in Grenoble at the CIA. So they provided us with the technique. And then what you have to do is a kind of reconstruction technique. So you measure Bx, By, Bz, and this is very important to get the three information for the efficiency of reconstruction. And then from the B is, as we know, related to the current density by the Biot and Savart law. And you can try to invert that. It's not an easy mathematical problem, this inversion. You have to take into account some constraint, but especially if it's not an arbitrary current distribution. But hopefully, you know a little bit where you are, your current. And from that, you get the distribution of the current flowing in your microcircuit. And this is quite important, for instance, to detect failure detection in microcircuits. And unfortunately, we didn't patent it. But now it's a product by Zeiss. It has all been employed after our work to do some very beautiful work to try to understand how the current flows in 2D materials, such as graphene or other materials. So it's really a tool somehow to investigate properties of current properties with a resolution in the micrometer range. And of course, the same technique will also be applied using scanning magnetometry. But for microcircuit, you don't care about. That would be the resolution is not what you want. You want to detect, for instance, a failure of the circuit. And this can be easily done with this technique, as you can imagine. Okay, and just to conclude this first part, that has led to a myriad of other developments. So I couldn't cover that. It's not possible at the moment. Each of them would be a given lecture, so, and maybe 2 lectures even. So for instance, people have used NV centers for atomic nuclear magnetic resonance. So now you want to measure the coupling to other spins, nuclear or even electronic spins that are just above the sample. And you can use a single NV center, or you can use the thin layer of NV center. There's a lot of possibilities on using that. You can associate that to microfluidic channel so that you can have a lot of experiments that are being developed on this direction. You can build also spectrometer, system that will measure magnetic field with that are tiny and that with the goal to compete at one time with the most sensitive system for that, which are based on atomic vapor cell that have a sensitivity of femtotesla per square root of Hertz. For the NV sensors, the best systems have now reached picotesla per square root of Hertz, but there can be other application. Then you can also, this is a beautiful work done in Delft and in Stuttgart in the team of Tamigno and Wartrup, in the teams of Team Tamigno and Jörg Wartrup, where people have used now the coupling to a nuclear spin. I will just describe a little bit how this coupling can be done. Carbon-13, nuclear spins, all that, and you can have a rich environment, and you can now address all these transitions and use them as a quantum simulator using all these spins that are used, and you try somehow to do something that competes with other quantum simulator based, for instance, on Rydberg atoms or other systems. I will spend now maybe 3/4 of an hour to finish. We take a break, and we will continue after that with application of NV magnetometry to sensing under extreme conditions, and that's a work that has been done with a team at the CA led by Paul Loubert. Thank you.